Welcome. In this video, we're going to discuss some of the pivotal theorems of calculus. Calculus is different from the math that your students have done in the past in that the conceptual ideas are much more challenging than the computational tasks. We will go through these pivotal calculus theorems and discuss how we can help our students better understand these ideas. The mean value theorem is one of the most important ideas in calculus. Essentially, the mean value theorem tells us that for a continuous function, the average rate of change on an interval must equal the instantaneous rate of change somewhere in that interval. In math terminology, we're saying that f prime of c is equal to f of b minus f of a over b minus a for a continuous function on the closed interval from a to b and differentiable on the open interval from a to b, and where c is between a and b. Let's take a look at this idea graphically, and then we'll discuss how best to express this idea to your students. Alright, let's take a look at some unknown function which is continuous on the interval from a to b. Now, if we draw this secant line from a to b, that's the average rate of change of the function on the interval. Now, what does the mean value theorem guarantee? Well, the mean value theorem guarantees that there's some c between a and b where the instantaneous rate of change is the same as this average rate of change. So what does that look like? Well, instantaneous rate of change is a tangent line. So what we're saying here is that there is somewhere on this curve where the tangent has the same slope or is parallel to the secant that we've already drawn. And you can see very clearly that there is a point like that. Now, this property seems pretty straightforward. So let's talk about the best way to help our students understand the finer details of the mean value theorem. One way to do this is to explain the basics. The derivative is equal to the average rate of change, and then challenge your students to come up with a function which does not satisfy this rule. Don't tell them that it has to be continuous or that it has to be differentiable. Let them explore. And the students will find that the only way they can create a function that does not satisfy this property is to either create a function that is not continuous or that's not differentiable. And this will help them to see on their own why these restrictions are necessary and these conditions are necessary in order to satisfy the mean value theorem. First, take a look at a function like f of x equals 1 over x squared on the interval from -2 to 2. Now, the average rate of change on this interval is 0. But of course, there is no point in that interval where the slope is 0. This, of course, is because this function is not continuous on that interval. So, by showing your students this, they will see that continuity is a key idea toward satisfying the mean value theorem. If you'd like, you can use the same problem and show them on a different interval, like -3 to -1, where the mean value theorem is satisfied. Now, let's take a look at an example which fails on account of not being differentiable on the interval. Take f of x equals the absolute value of x minus 3 plus 1 on the interval from 2 to 5. Now we can see here that the average rate of change is 1/3. But it's obvious that an absolute value function has either an instantaneous slope of 1 or -1. So it can't satisfy the mean value theorem. And that's because we have a cusp. A cusp means that this function is not differentiable on the interval, and of course, again, fails the mean value theorem. These are just a couple of great problems you can do with your students, which will hopefully help them understand how and why the mean value theorem works. The squeeze theorem, often called the sandwich theorem, is one of those rare times where something extremely useful and extremely logical intersect. Let's take a look at what it is and how it works. The squeeze theorem is used for evaluating difficult limits which may not be easy or obvious to evaluate with other methods. The idea here is to take the function you're trying to evaluate and sandwich it between two other functions. One which is always greater than or equal to your function, and one which is always less than or equal to your function. Let's take a look at how it works graphically. You can see that the way we create these functions, there's one function always above, one function always below our given function. What's important here is the point where these two functions come together. We are creating these functions, so we're going to make sure to create them in a way such that they come together at exactly the point where we are looking to evaluate our limit. This is like a limit hack. Instead of dealing with the complicated function we were given, we're taking these other two functions and showing that at the critical point we're looking for, they come together and are equal. And since they have the same limit at that point, and our other function is in the middle, it must also have the same limit. Consider the limit as x approaches 0 of x squared cosine of 1 over x squared. Now upon initial inspection, the answer is inconclusive. We get something unknown. So let's try to use the squeeze theorem to help us. We know that no matter what x is, the cosine of 1 over x squared is bounded between -1 and 1. So let's set up an inequality. -1 is less than or equal to cosine of 1 over x squared is less than or equal to 1. Now let's multiply everything by x squared so we end up with our given function in the middle. -x squared is less than or equal to x squared cosine of 1 over x squared is less than or equal to positive x squared. So what we've done here now is we've sandwiched our given function, which is complicated and messy, between two simple functions, -x squared and x squared. And since the limit as x approaches 0 of both -x squared and x squared is 0, and our given function has to be in between them, then the limit we are looking for must be 0. Alright, now for the biggie, the fundamental theorem of calculus. The fundamental theorem of calculus in essence guarantees that integration works, and that it gives us the area under the curve. Without the fundamental theorem of calculus, we might still be calculating areas with Riemann sums or worse. Unfortunately, the proof of the fundamental theorem of calculus is quite long, detailed, and complex. It's unlikely that it would benefit most high school students. So instead, what I'd like to show you is a sort of conceptual proof. We'll run through many of the arguments in the true proof, but without attending to every detail. First, we need to explain to our students that may already have some idea of what an antiderivative is, that for the purposes of this problem, we don't yet know about antiderivatives. In fact, that's what we're going to try to prove with the fundamental theorem of calculus. So we start with the graph of a function like this. And we're going to consider two areas under the curve. The area from a to x, and the area from a to x plus h. Now, we can write those areas as integrals. Even though we don't know how to integrate, we can still write them as integrals even though we don't know what an antiderivative is yet. What we want to focus on is the area between x and x plus h under the curve. So this creates a definite integral, which is what we're trying to prove. What we're going to do is we're going to create a new function which represents the area under the curve. Let's call it g. So g of x would be the function that gives the area under the curve from a to x, and g of x plus h would be the area under the curve from a to x plus h. So what we're really looking for here is g of x plus h minus g of x. That will give us the area between x and x plus h. So this is actually equal to the integral of our function from x to x plus h. So now the last thing we need to do here is we actually need to use the squeeze theorem, believe it or not. If we look at the area under the curve, we can actually create a minimum possible area and a maximum possible area by creating two rectangles, similar to the way we do it with Riemann sums. Our actual area will be sandwiched somewhere between these two. Now if we divide everything by h, we should start to get something that looks a little familiar. Now, all we have to do is take the limit as h approaches 0 and check out what happens. Well, the upper height and the lower height are going to become the same since h is approaching 0. And that height we would call f of x. And in the middle, this limit is precisely the definition of a derivative of the function g. So what we've done is we've squeezed the definition of a derivative of g between the function f of x and shown that the derivative of our area function is the value of the function itself, or conversely, the antiderivative of our function gives us an area function. The fundamental theorem of calculus is a very difficult concept to explain to your students. Don't be discouraged if you don't feel like every student really gets it the first time. The idea here is not to waver from best practices, which tell us that explaining is better than just telling. Below, you'll find some additional resources which may help you in explaining this topic to your students. Remember that even the students who don't completely understand this proof will still benefit from seeing this critical idea proved, and knowing that it's not just something written in a book, but actually something that is logically developed and connected to previous topics.